Okay, continuity and in behavior. Do you guys remember any of this from last year? Okay. If I say something is a function is continuous, not quite.
It's not continuous.
Oh yeah, it doesn't have breaks like little.
There we go. No breaks or holes or anything. So this function is, let's call it f. F is continuous. On its domain here. Okay, so we haven't defined any of it. So conceptually, when you draw that graph, do you pick your pencil up?
No.
Okay, so that's kind of a basic litmus test. Okay. So when you draw it, you don't pick up your pencil, it's continuous. If you drive to Denver without stopping, would you consider that a continuous function?
Yes.
Okay, what if you pulled off in Silverthorne and ate lunch?
No.
No, because there's a break there, right? In the distance and time relationship. How about bank account interest? Is that a continuous function? See, I put $5,000 in a bank account, and once a month it earns interest. Is that continuous? Uh-oh. Fight.
Yeah.
Why?
Because it doesn't stop. You don't stop earning interest. It just keeps.
Well, because the interest grows each month because you have more money in your bank account.
Okay, the interest only compounds once a month. So is it continuous? Okay, so let's say you have $5,000 and it's January. Then you get your interest here. Does it smooth curve up or does it just make a jump? Okay, it does. So maybe now you have $5,010. And that's an instantaneous jump. So not continuous. If I were to draw. So this is one type of continuity that you'll see. It's called a jump discontinuity. And so it just jumps from one spot to the next. Piecewise functions are classic for having jump discontinuities. There is also an infinite. Thank you. Holy cow. There we go. Infinite discontinuity. Okay, this. Zach, I can hear you still.
You want to hear what we're talking about? I mean, it's not private.
Whether I want to or not, it's happening. Here's the last one. It's called a point discontinuity. I'm going to do this function. Okay, there's just a hole. Just as an aside, if we factor the top there, do you notice how the top and the bottom are the same in this term? If that happens, with the same thing top and bottom, all we have left is this. That's the graph, y equals x minus 1, except as a whole at x equals -1, because of that relationship there. So that's when that occurs. I'm not going to hold you to that, but that's FYI. Let's see. Here's an example for you. F of x equals 3x squared plus 7, continuous at x equals 1. And I'm going to show you how to test for continuity through this example. Okay, so first, is f defined at x equals 1? How am I going to test that? Yeah. Check. The next one okay, this is something that you've probably never seen. Does f approach the same y value, 10 in our case, from the left and the right? I'm putting it back. Okay, so I'm going to draw the graph for you because it'll make this a lot easier. What's the y-intercept? Let's go by 4s. It's 7. Plus 7 there. If x is 1, we have a 10, -1, 10, so it's going to look something like this. You can do that with parent functions as well, or families of functions. So we're looking at x equals 1. That's right here. What happens from the right? And a different color here. From the left. As we come into that point, we're approaching it from both sides. It's kind of like walking towards the wall. What are you going to hit eventually? The wall, right? From either side. Okay, the question is, does the wall exist? And is it 10? The writing's on the wall. We don't need no education. Is that what he said, Bess? Nice. I didn't think I'd throw that one in there, did you? Numerically, okay, pay attention here. So from the left, I'm approaching 1, right? So I'm getting closer and closer to 1. 0.9, 0.99, 0.999, right? That's getting closer to 1. What happens to f of x? So if I plug those in, I'm just writing them out of the book here. We're not going to take the time to calculate. Is it getting closer to 10? Right. Okay, from the left, it's going to 10. And the right, do you think it'll do the same? I agree. So that would be closer to, okay, we're getting closer to 1 from the right side. The y values. Are going to 10, right? So continuity, there's one more test that we must meet. Are you okay with the first two? Okay. I'll wait because I'm going fast. These, I put 0.9 into the original function. It's close to 1. On the left side of 1 is 0.9, right? And then you get closer, 0.99, then 0.999. So what it looks like on a number line, here's 1. You say 0.9, 0.99, 0.999. So you're getting closer from the left. And then 1.1, 1.01, 1.001. You're getting closer from the right. So we're going towards it. Okay. So as x approaches 1, f of x approaches 10. Okay, that's test number 2. So 1 and 2. The third one is the easiest. Do 1 and 2 match? Are they equal?
What do you say? What I get here and here? Check. Okay, so f of x is continuous at x equals 1. Okay, that's just at that one spot. A little bit of work, isn't it? I'm not concerned that you know how to do number 1, but I know that number 2 is new to you. That's a calculus concept. Doesn't mean you need to be confused. Basically, what's happening around that point. Okay. So you can do that one graphically or numerically. There are a couple more examples in your book. I encourage you to look at those. I don't want to take your time. Okay. Because we need to get to work. But into behavior. Yeah. Into behavior is very straightforward. And you guys did a fine job on it last year, so it should be pretty quick. Basically, I've been asking you to graph something and describe what happens towards infinity. Yeah. So okay, what happens as x goes to infinity? That's positive direction. What's happening to the y? Okay, we're going to put f of x goes to infinity because that's what our function is defined as. What about this side? Happens as x goes to negative infinity. Yeah, it goes up still. All right. Do you need any more than that? There are cubics and upside down quadratics, absolute values, all sorts. If you can graph it, it's the same thing. You just have to be able to describe it. Okay. The last thing is increasing, decreasing functions. This was on the sheet I gave you Friday. I think most of you understood it from the So we go left to right. Basically, we're describing what's happening with the graph. All right, so left to right, this is coming down, correct? We call it decreasing. And then right, left to right, increasing. Feel free to use your calculators to graph these, of course. How about this one?
That's cute.
Oh, I know. It's beautiful, isn't it? Okay, where is the graph increasing? The left side, can you be more specific? Like give me an interval? It starts here, correct? Now it's increasing. Where does it stop? Okay, so we go negative infinity to negative 1. This is called an interval. I introduced you to that Tuesday, I believe, barely. And where else? 1 to infinity, here. And then decreasing, negative 1 to 1. Those are your boundary lines. Okay. Decreasing. Now we're out of Redneckville. So again, describing what functions are doing. Are they continuous? What happens towards the ends? What happens in the middle? You're just describing graphs. Okay. The challenging part of this is continuity, proving continuity. And page 160 has a couple of more examples you might want to look at. 3 actually. So, do you have any questions? You get the idea? Sure, or yes, or what the heck are you talking about? Or okay, I guess we're gonna find out, aren't we? Yeah. Let me try to get the work up here. Huh? Yeah. One through 9 odd. 14, 18, 24. Yeah, you guys should be pretty good on this one. I just looked at it again. It's the only real challenging part is proving continuity. That's only a couple of them, so give it a start. You might start with number 5, just to make sure you understand it.